As a specific example of some research that's focused on this variety problem, one of the systems we've been building in my research group is something called MapD. So MapD is a really very super efficient system that's designed to process social media data, specifically looking at tweets. So you guys probably all know that tweets are 140 characters long. Some things you might not know about tweets is that a significant fraction of the tweets in the world have a location attached to them, so you can put them on a map. You can see where the person who wrote that tweet was writing it from. This data typically comes from the position sensors on smartphones. Every day in the world, there's something like 5 to 7 million of these geocoded tweets that get produced. So there's hundreds of millions of tweets, and some small fraction of them have these positions, geocoded information with them. So what we do in the MapD system is plot all those geocoded tweets on a map over some period of time, and then allow users to interact with them and search for things in them, to browse them and animate them. And some specific examples of things that you can do with MapD are to see patterns of diseases or patterns of weather as they spread across the country, because people will tweet when it's raining or snowing, or when it's very cold, or when they have a cough or the flu, or they're sick, or they went to the doctor. And those things can be visualized on a map and seen in a very compelling way. So this is a big data challenge, and in specifically it's both a variety and a velocity big data challenge, because there's lots of these tweets, they're arriving in real time. You want to do these animations of the data. The animations aren't pre-canned, they're not pre-computed, but they're done on the fly as users ask questions about specific words. And the data that's being processed here isn't conventional tabular data, it's these words, it's text, and so you need different ways of sort of pre-processing and consuming and formatting that text in order to make it into something that's computable on by a computer. So you need to convert it into these maps that have density visualizations of the tweets in different regions of the world, or word clouds or histograms that talk about the frequencies of different words over time. And so there's a lot of sort of complexity associated with doing that sort of pre-processing. So another big data research project that we've been working on at MIT is a project called SciDB. So SciDB stands for Science Database. And the idea in SciDB was to try and build a database system that's targeted towards applications that conventional relational database systems aren't very good at. So relational database systems have been focused on these very boring business processing applications, and actually my research is focused on this area, so I feel okay calling it boring. But the things that these conventional systems tend to be good for are business analytics, reports, those kinds of things. The idea with SciDB was to say, could we build a system that had some of the capabilities of a database system, like a really easy to use query language and really efficient ability to process large amounts of information, that was more targeted towards a class of scientific applications. And the sort of most salient feature of SciDB is that rather than thinking of the data as being tables, we think in SciDB of the data being arrays or matrices. So these are multi-dimensional structures that you can run matrix algorithms or operations on. So examples of things that you might want to do with SciDB are, for example, some genetics or genomics applications, where you think of a matrix of patients on one dimension and genes on another dimension, and then you're doing various kinds of statistical analyses of those matrices in order to find patterns or to find genes that are specifically correlated with patients that have certain conditions or outcomes. So SciDB is a it has a high-level query language that allows you to express these kinds of operations over these matrix structures, and then it very, very efficiently processes these queries on either one machine or a large number or a cluster of machines. And so this is a big data challenge because it's going from these conventional data processing applications to a much richer and I think more interesting class of applications that focuses on what scientists need to do. And oftentimes the data that needs to be processed here is very large, and the complexity of the algorithms is very high. So it's, I think, a challenging and interesting research area. Another example of a big data system that we've worked on at MIT for several years is a project we call Cartel. This is in car telecommunications, not drug cartel. The idea in Cartel is originally was to deploy sensors on moving vehicles like cars and buses in order to measure things about the urban environment. So for example, to measure what traffic looks like, or to build maps of radio connectivity, either Wi-Fi or cellular connectivity in and around the city, or even just to measure the patterns of movement as people move around the city. So what do commute patterns look like and other things. To give you some examples of some of the challenges on the computer science side that arise in a system like Cartel, when you have vehicles that are moving around that need to communicate with each other, you need to figure out how you're going to get data off of these. And you might use an always-on or persistent cellular connection, but then that would require deploying an expensive cellular modem in every vehicle. So we've looked at doing things like opportunistically connecting to Wi-Fi networks as cars drive by them, or developing networks, multi-hop networks of vehicles that communicate with each other as they pass each other on the road in order to exchange pieces of information.